shiny because you've got all the volatiles off. If you crush it, it should be pretty brittle. And if you dust your hands, you'll be able to get it off fairly easily. That's kind of an indication that you got a pretty good biochar, and it shouldn't have any smell. If you get kind of a sour or a nasty smell coming out of it, there's still some volatiles in there. So it should be a pretty dull smell.
Our speaker today is Chris Olson. I have to pull up his bio because, you know, that's how we roll. So Chris has worked for the past 7 years in the waste management and alternative energy space. You might remember Chris from years ago when I was working at the town, and we had actually the launch of Walk the Talks. I think, Chris, you came to a couple of our sessions, didn't you?
I believe I did, yeah.
At the very beginning. And so Chris has worked for the past 7 years in waste management and alternative energy space. Chris is an alternative energy technologist with a sociology degree. And he has, over the past 7 years, has clarified his passion for sustainable practices, processes, and technologies. IRSI, the company that you own, Chris?
Yep.
That you own, that you're the primary in, drive towards revolutionizing the handling of residual biomass waste streams, and is aligned closely with Chris's personal passion for improving the waste management and sustainable technology space. Chris has worked closely with private and public organizations to develop projects aimed at reducing greenhouse gas emissions, improving waste management practices, development of leading edge renewable technologies, and cultivation of a well-informed understanding of a variety of bioproducts. Chris has experience raising both public and private capital and has worked with Alberta Innovates, the Industrial Research Assistance Program, MITAX, NSERC, as well as a number of private companies and associations, some of which he will talk to us about this evening. So with that, since you're all muted and he can't help you clap, he can't hear you clap, maybe you can just welcome him by clapping like this. Please welcome Chris Olson.
Well, thanks a lot for the intro there, Mark. And first off, I just wanted to thank Mark and Heather for thinking of me and including me in this. And I wanted to give you guys all a lot of kudos as well. I think these sorts of events are really important. And I think getting information out for people to digest and think about is a great way to go. So kudos to you all. So the first thing I just wanted to kind of jump out and give you guys the overview on is that I will be speaking about biochar, but it'll be about halfway through my talk. So what I'm going to do here first is kind of address the All West Bioindustrial Park, which is a public and privately funded project that I put together with 3 other companies. That's been carried out over the last year, and we've got about 14 months left operating here in Edmonton. So I'll kind of start with that, and then I'll get into specifically what IRSI is doing and the technology that we're running. The other thing I did tell Mark as well is that if anyone has any questions while I'm talking, sometimes I kind of go a mile a minute. If you throw them out there and Mark sees them, I told him just to have me put the brakes on, and I can answer any questions kind of on the fly there as well. So if anything pops up, feel free to ask. So as you can see from my first slide here, I'm looking at waste management as a global problem. It's something that we all have to deal with. Every country on the world, every region in the world, we all have different waste streams that we produce, and we have to come up with innovative ways to solve them. So the problem that we've identified is the waste management issue. According to World Waste Facts, collectively we throw away about 2 billion tons of waste per year. Statistics Canada in 2016 found that Alberta alone contributed about 4 million tons of waste to landfills. We actually have the highest per capita waste disposal in our country. So for whatever reason here in Alberta, we seem to waste a bit more than other people in our country do. That 4 million tons is approximately 250 million in gross disposal fees at $60 a ton, which is a little bit below the provincial average. In 2015, according to Statistics Canada, the top waste management companies in North America generated about $7.3 billion in revenue. So waste is quite a profitable industry, and there's a lot of opportunity there to come up with better ways to manage that, and that's part of what we're trying to do. So the opportunity and how we're looking at it, we're looking to reduce landfill material and reduce disposal fees. We're looking to increase revenue generation from improved practices. So not only are we running thermal treatment equipment, but working with All West Demolition, who is the lead applicant and the owner of the yard that we're operating at, We're trying to sort their material and come up with better ways to divert it. For the last 5 years, they've been diverting concrete and metal because there's a market for it. So they're actively doing that as a transfer site. We're just adding a little bit more to what they're able to do on the park. One of the other potential opportunities is decentralized power production in regional locations. Here in Canada, we don't do it quite as effectively as other parts in the world, but if you go to Europe, Stockholm is entirely run on a waste energy district heating loop, and Pyreg, an Austrian company, actually has a pyrolysis process that's piped into that heating loop. So they're using pyrolysis to actually heat homes with thermal energy right in the city. Also looking to reduce greenhouse gases. Anywhere we can offset petrochemical consumption, we can reduce greenhouse gases. If we can avoid landfilling material, we can reduce greenhouse gases. We've done a full LCA life cycle assessment for our activities at the park, and we are able to show that for each ton we keep out of landfills, we have a measurable impact on greenhouse gas emissions. The bioproducts and the additional revenue that comes with those materials, we specifically are aimed at producing a biochar, but there's additional other materials that you can produce, activated biochars, plastic additives, compost materials, soil amendment, fertilizers, all that sort of stuff. Job creation. So over the last 12 months, we've employed about 7 or 8 highly skilled laborers doing everything from metal fabrication to programming our electrical components. I have 2 highly skilled engineers that work with me and do some of the computational fluid dynamics work, as well as general laborers. We got about a half dozen guys that work with us on site when we're operating the equipment. I really am through this project and with one of the colleagues that has put this project together with me, and was actually the guy that introduced me to Mark, Tom Ogarenko. We've really tried to focus on the integration and collaboration as being essential to making this work. Not just the technology, but the skill sets and the expertise. That's really a focus of what we're trying to do with this project. So the solution that we're looking at is the All West Bioindustrial Park. It's located off 75th Street and 64th Ave here in Edmonton. You can check us out at awbip.com. And the company's, my company, IRSI, on the top right there, All West Demolition is a prominent demolition company that's the lead applicant on the project and is home to the location that we're at. And then Nelson Environmental Remediation is a leading soil remediation company that has a very similar technology to what we operate for indirect pyrolysis. And I can't stress enough the support that we've gotten from Alberta Innovates, not just from their funding group, but also from their applied research arm, which is Initech Alberta. They've helped us with this project, but also with other projects in the past. And I can't speak highly enough about the support that I've gotten from them. So the All West Bioindustrial Park. It's intended to be an industry-led bioindustrial ecosystem that is aiming to drive commercialization of innovative technologies, processes, and products through the collaboration of business, academia, researchers, and government. When I got started doing this about 6 years ago after I'd fabricated my first system, we looked for about 8 or 9 months to find a space to field demonstrate the equipment. And it was really quite a struggle just to be able to get somewhere and do some testing and essentially find out that we had built something that didn't work all that great.
Sorry, Chris, before you go any further, could you talk a little bit about what got you into this idea of your product fabrication, like why this came up for you?
Yeah, for sure. So after I finished my sociology degree in Calgary at the U of C in 2009, I came back to Edmonton and I took the alternative energy program at NAIT. During that program, I was also working as a environmental manager for a waste hauler here in the city. And we ran in our 4th semester a group project that got us a downdraft gasification system. That downdraft gasification system was my first experience with thermal treatment processes. And through that project, I was able to show that we could reduce the volume or the weight of residual waste streams by about 80%. And as I was going through the lead reporting for the waste hauler that I was working with, I guess a bell just kind of triggered in my head, leading me to, there's about 60 or 70% of the material in a construction and demolition waste stream is typically biomass. And there's a lot of potential for that material. So that was kind of the genesis for me back in 2014, launching IRSI and getting into these thermal treatment technologies. So NAIT was a big part of that for sure.
Awesome, thanks.
Yeah. So the All West Bioindustrial Park, it's an 18-acre site. Like I said, they're off 75th Street and 64th Ave here in Edmonton. We've got about 40,000 square feet of indoor space, overhead cranes, all the utility plumbed in, and we've got about 2,500 square feet of shared office space available as well. We've got equipment on site, excavators, shredding equipment, separating equipment. We have engineering capabilities. I employ 2 engineers on site myself. There's metal fabricators that work out of the yard, and a number of other trades that are also there. This picture along the bottom is kind of a 180-degree view. If you drove by it on 75th Street, other than seeing the big All West demolition sign, it would look pretty normal. Once you drive into it, though, it's a whole crazy mess of things going on, and it's quite a large space that runs pretty long down the 18-acre site. So the setup of the All West Bioindustrial Park, kind of the core group that was involved, I've mentioned Alberta Innovates, but I just wanted to mention them again. So their instrumental support around the CCITF facilities project that we applied for. Their 3 main goals were advancing technologies that benefit Alberta industry or public sector, supporting novel technologies with the potential for greenhouse gas reduction, economic diversification and employment, and recruiting and developing highly skilled personnel in emerging clean technology industries. Over our first 12 months, we've been able to do this, and we're going to continue to be able to carry this out over the course of this project. And this is the kind of support that I think Alberta Innovates serves a real instrumental role in providing for clean tech technologies and a lot of pre-commercial, pre-revenue technologies such as IRSI. So All West Demolition, I've touched on a little bit here, but I'll just go into a little bit more detail. So they've been operating out of Edmonton since 2009. They handle on average about 20,000 tons of waste per year. Most of that waste material comes in the form of construction and demolition waste, things along those lines. So for anybody who doesn't know, you'll typically group different streams of waste materials into everything from recyclables, cardboard, plastics that are separated out, to construction and demolition waste on demo sites. So you'll get mostly wood material, insulation, some plastics, some asphalt, some concrete, some brick, that sort of stuff. Anything that would come in a house that you tear down. And then you have source separated materials, so clean concretes, clean metals, that sort of stuff. And then general garbage is typically referred to as MSW, municipal solid waste, which typically will go into like a compost process if it can, or will try to be recycled in some form. So we mostly deal with residual biomass materials and construction and demolition waste coming from All West. All West currently employs about 30 to 40 full-time staff. They're seasonal, so in the summer they'll ramp that up to around 49, 50, and then sometimes in the winter when it's a little bit slower, they'll be down to that 30. With their senior staff, they've got about 100 years of experience, and they like to say around the yard that smashing is their passion, so they like to break stuff. That picture there at the bottom of the image in front of you, that's the Walterdale Bridge. So it was actually All West Demolition that took that bridge down a few years ago when that project was going. So on site is really where it starts for us with the park. A lot of demolition companies will move as quickly as they can to take buildings down, get it into waste bins, and get it off site. We have been working with the All West team and their operators to make sure that when they take buildings down, they're doing it with intent. So something as simple as when you tear a house down, if you don't dig up the concrete foundation, you can separate out that concrete. So A, it doesn't get blended in with the wood material that we could utilize, and B, you actually have a potential revenue stream from that concrete as well. So there's a lot that goes into how they do their work, and how they really think about bringing that material to the site so that when we need to process it, we're a little bit further ahead. Now, it does take them a little bit more time potentially to do that at site, but it saves us on the back end because we don't have to process material quite as much.
And
So
I think it saves them some money as well, doesn't it? Like a little bit more labor on the upfront, but then they can separate the concrete and get money for that, as well as then separating out the rest.
Yeah, 100%. And that's what we're trying to add is giving an option for the biomass material, because for concrete and metal, there's a market for it. So the back end of the site is probably about 4 acres of different aggregates. So they crush up their concrete. They'll sell that back to people who actually produce concrete as an aggregate. And they'll also take in material from other people as well. Same thing with metals. They'll sort out all the metals they can, they'll stockpile them, and then typically whenever they can get the best price, they'll send that to Maple Leaf Metals, which is actually just a stone's throw from where we are. I think they're just off 50th Street in Ellionac in Edmonton. So once the material is brought to the yard, that's where we start processing it. And the front end pre-processing is done by All West for us at the site. So they'll do manual sorting of waste streams. So some of their operators are quite capable with an excavator, much better than I could ever be operating that heavy equipment. And they'll actually start pulling out large pieces of wood material that we can separate out into our clean wood pile for our pyrolysis process. They'll also do shredding of the material to get it to an appropriate particle size. Our gasification equipment needs about 4-inch nominal, so average size under about 4 inches, whereas our pyrolysis process, we wanted about 2 inches. So different materials going into different systems will shred to a different particle size. They'll also trommel our material, so they'll screen out some materials. The fines that we get actually have some applications for different sites. So some landfills will take the fines as an alternate daily cover. So it helps control odor at the landfill, helps with gases leaching out, that sort of stuff. So what we're also trying to do is really sourcing different uses for these materials that we can't process ourselves. So once we get it, our goal is to really landfill nothing. Now, we're not there yet, but as we go through our process, we want to identify as many opportunities for any of these other residual materials that we don't particularly have an application for. We've talked with different biocomposite groups. We've talked with people doing things around improved concrete, reduced carbon intense concrete applications, and there's potential uses for a lot of this stuff that we can get out of the site. So Nelson Environmental Remediation is a key partner in this project as well. NER was an Alberta born and bred company that has been operating since the 1980s. They're globally recognized as leaders in direct and indirect soil remediation. They do a lot of work all over the world, a lot of work in the United States. They have projects in China, and they actually don't hold any patents on their technology, which is kind of interesting. It's all trade secrets. So you could copy their technology, but you don't know how to run it. So the skill set and the expertise that they have goes a long way. And we've been very fortunate with Warren Nelson specifically supporting us with some of the work that we're doing. So Warren and his brother Daryl have led NER since 1994. They currently maintain the largest fleet of thermal desorption units in North America. So I'll kind of explain what those thermal desorption units are here in the next slide. Many of their upper management staff individually have 25 years of experience, and they probably have about, I would say, 50 to 60 staff at any given time that they work with. Over the last few years, they've been developing a focus on environmental stewardship, and part of that is what we're doing with them at the site. So if we can find them an alternative low-quality biomass material that could replace a diesel or a propane or a natural gas, then that has some value for them and has some other benefits as well. The last comment here, so their indirect thermal desorption units are very similar to our piece of equipment that we're running at the site. So what exactly is an indirect thermal desorption unit? So this site, I think this was in North Dakota, I believe, in the US. And so what you're looking at here is a thermal oxidizer, a combustion chamber, and an indirect remediation system. So on this site, they're essentially burning, I think they were trucking in diesel here, and they're burning diesel to get thermal energy. They're then driving that thermal energy into a indirect remediation system, which is the black system on the right. That's then remediating the soils, essentially exposing it to a high heat without any combustion taking place. And then the volatilized off gas, the gas that is removed, comes into the combustion chamber and is combusted there. Some sites, they can condense out that syngas or that producer gas and get a liquid fuel. It really depends on the scenario, the customer they're dealing with, whether they want the fuel back. And then typically the inert soil that comes out on the back end, they then fill it back into the hole that they dug it out of. So these are sites where there's been an oil line that's burst, there's been an oil rig that's leaked, something along those lines. They get called in and they do the work and then put the soil back in the ground. So the activities that they are carrying out on our site, this is the setup of the equipment that they have. So they're looking to get to prove the concept that they can use low-grade biomass to remediate soils and use that thermal energy. So what we're looking to show with our equipment at our site, working with NER, is that you could take something like contaminated soil at an oil spill site or railway ties that are fairly common at those sites. You could shred those up and you could process those through something like our equipment, the gasification technology that we're running, use that thermal energy and then drive that energy into an indirect system to remediate their soils. So this setup that they have here, the picture on the left is the green box that you're looking at is a modified thermal oxidizer. And then that ducting going off to the left of that is driving thermal energy into an indirect double auger system. So that would be on the right picture, the black box just behind the gentleman in the silver vest. So what they're doing here is showing that they can indirectly heat this process and they can operate this way. And then once they validate this, they're going to come to our site and they're going to use our gasification system and our pyrolysis equipment to actually remediate soils to show it as a proof of concept. So when I first met with Warren, probably about 3 or 4 years ago, we had a 3-hour dinner and he asked me just to kind of run him through everything that I was doing, very similar to what I'm doing with you guys now. And about an hour and a half into the conversation, Warren kind of laughed and he said, you know, Chris, I think I have the largest biochar production system. It's just not producing biochar. So their technology is very similar to what we're running now. And it's been a real benefit to us to having them working with us and providing their expertise. So another part of what we're doing at the site, and I mentioned Tom a little bit earlier, Tom Ogaranko had worked with Mark in Devon and had done some of the challenge dialogue work. And that was when I first met with Mark, actually, which probably about 5 years ago now. Geez. Yeah, at least I think. You're on mute there, Mark.
Yeah, I believe it was 4 or 5 years. It was 20, yeah. I think it was January 2016, I think.
Yeah, that sounds about right. So the challenge dialogue system, and some of you might have had some experience with that process, is a proven framework to help diverse groups collaborate and innovate to accomplish complex tasks for change and transformation. So the real great piece of the CDS methodology is that it's for problems or challenges that there aren't readily available solutions for, that typically need a number of perspectives to get a good handle on. The example that I'll use just to walk you through this 8-step wheel, we looked at doing a waste characterization challenge at the park when we got started. So we identified early on that we need to be able to, as best as possible, identify the different composition of waste streams coming into the park. So if there's a construction and demolition bin, if we can tell that approximately 60% of that bin is biomass, it's worth us picking out that wood material. If it's 20% biomass, it may not be worth it. So we wanted to be able to identify waste streams as they came into the site. So the next step past that was to plan that challenge. Okay, if we want to be able to do that, then how do we do it? The method that we use for that is writing a challenge paper. So it's a 10 to 15 page document that lists assumptions that you're making, critical questions that you need answered, expected outcomes for the dialogue, and states a key statement, a key challenge that you're trying to address. And then the next step is to identify participants, people that you want to bring in, people that you want to get input from, and people both in your supply chain or within the sphere of expertise that you need, and ideally people outside that sphere. So again, for the waste characterization, it's great to have people that provide technologies, infrared technologies, imaging systems, IoT, but it's also important to have people outside of that technology expertise to talk. So we had the All West guys sit in on the conversation, myself as well, giving my 2 cents on what that activity was. You then go through the process of sending out an online survey, seeking input from the stakeholders that you have involved in the process. You then refine that challenge paper, and then you get another iteration of that out, and you get into typically a face-to-face workshop. So then you sit down face-to-face, you get as many people in the room as you need, and you go through testing that understanding, testing that challenge, and making sure that you have the right criteria in place. And the end goal with this specific process is to get essentially a request for proposal out to industry and out to your supply chain to hopefully get a solution. I've gone through about a half dozen of these over the last few years with Tom. And I've seen some really, really terrific responses. And it's really an interesting way to go about it. And I really like the collaborative and the integrated approach to looking at these challenges through the CDS methodology. So the advantages that you get out of it, and some of them I've touched on, you accomplish more in less time. You do a lot of things online. So you typically have consultants who are assisting you with it. The CDS network is a wide-ranging array of consultants all over the world that can work together on different projects. I'm working on one right now with Tom, as well as the industry stakeholder that's involved, so they get a very key role as well. So they'll put together your organizing team, and they'll make sure that they're on point, they're moving through the right way. But it's that back work of going through background information and testing those assumptions and getting all that input from everybody before you go face to face. So you do a lot of work leading up to that face to face first workshop. The application of diverse perspectives to complex challenges. So again, getting people who aren't necessarily specifically well versed in the very narrow challenge that you're looking at, but maybe have some alternative perspective that really adds a lot of value. Sometimes you get some of the best input from people who aren't necessarily in the area that you're looking to solve the challenge. The movement from idea to action is very expeditious, and it moves very quickly. So within about 6 to 12 months, you can actually get a testable demonstration technology out in the field and start testing it to see if it works. And then again, the diverse global out of the box thinking is a key piece of the CDS methodology. So specifically what we're doing here at the All West Bioindustrial Park is the rapid performance improvement process. So over 2 months, we do industry consultation. So what we did with the waste characterization study, draft a challenge paper, go through that process. You then go through selecting innovators. So go ahead there, Mark.
Oh, no. Just before you run on, we had
Sure.
a question about the remediation component on the soil.
Mm-hmm.
Are the soils that become decontaminated then useful for agriculture, or is it just fill?
Yeah, so they would come out as an inert soil. So yeah, they could be used for agriculture, but my understanding of it would be that they wouldn't have any microbial life. Most nutrients would probably be stripped out. So it'd be more of maybe an additive into an application. They maybe wouldn't have a tremendous amount of value on their own, but they're clean soils, so they're inert soils. So most of it ends up as backfill back into the site they're at, but they could be used. And that's part of what we've looked at as well. Blending a biochar, a compost, and a clean topsoil can get you a really nice soil blend. So that's something that we've looked at and definitely talked with NER about.
Okay, and a couple other questions that popped up is your site considered to be waste management site? If so, what were your challenges in permitting or auditing the site, or auditing for the site? Like, do you do tours of your emerging technologies?
Yeah, so we do. Right now, we're obviously with everything going on, we haven't had any tours in at least a month here. But yeah, we do. We bring people through. We are identified as kind of as a transfer site. We right now have a letter to operate from Alberta Parks and Environment for our technology at the site. But eventually we would be considered kind of a waste to energy site because we will be producing thermal energy at the site. So there's a permitting process for that. Because we have research technology that we're working with, we haven't gone through that full process yet, but that would be the end goal. We're not actually depositing any material into the land. So really we operate as kind of a transfer site, I guess would be the right way to put it.
Mm-hmm. Okay, cool. And then do you take bio waste from other companies?
Right now we don't, but down the road, that might be something that we look at doing.
Okay, terrific. All right.
So yeah, the industry consultation, and then there's an innovator selection. So you identify the people that you want to work with. You bring them in over 2 months. You give them the opportunity to test some of their technologies as well. You then go through the innovation sprint. So you get 3 to 5 prototypes developed over 4 months, and you get them ready to be tested in the field. And then over the next 6 months, you actually do field trials. So right at the site, part of the goal that we wanted with the park was to give technologies like myself, 6 years ago that are ready to field demonstrate, give them space to demonstrate. It's not necessarily going to be a permanent home for everybody, but if you need a bit of space and you need some equipment and you need some support, we could potentially be a really good site for you to test some of those technologies. And then eventually commercial launch. So if that technology is successful, then you get it out into the field and you carry that forward.
You make it sound so easy.
Tom makes it sound easier than I do. So when we put the project together, I just wanted to throw this in to kind of give you a bit of background on what Tessellate, Tom's consulting company specifically has done, and some of the work that I've actually been involved with them on. So in the energy and mining sector, they've worked with Rio Tinto, Shell, Statoil, ConocoPhillips, and Nexen. Innovation collaborators, they were actually involved with both the setup of COSIA and the OSLI Association, so some of the oil and gas guys here in Alberta. They have done some work with the Clean Energy Technology Center out in Drayton Valley, the International Minerals Institute in Saskatchewan, which is the association for the mining companies there, Bio Alberta, FP Innovations. FP Innovations is the forestry, what would the term be? The forestry innovators out of the Vancouver area. And then of course, our park, the All West Bioindustrial Park. Some of the accelerators that they've worked with, Foresight Arctic, Nova Scotia Innovation Hub, and the economic development. So obviously with the town of Devon, the town of Drayton Valley, the county of Grand Prairie, and then they've worked with a number of different funding agencies, some of which we've worked with as well.
So just so you know, the challenge dialogue that we did in Devon was the catalyst for Walk the Talks, because after we had finished off with our challenge dialogue system process, we realized as residents that we still had a ton of questions. And so Walk the Talks was formed because
Awesome.
of all the questions that happened out of the challenge dialogue.
Yeah, and that's typically what I've seen is that sometimes you don't even know you have the questions until you go through the process, and then there's all these other things that kind of come up. So yeah, that's terrific. So when we put our project together and put our proposal into Alberta Innovates, I did my best to get as much support as we could from different companies that I work with. And there actually was a number of people that were interested in working with us and giving us support. So the top two on the right, the International Biochar Initiative and Airterra, those are biochar related companies. Enercam obviously has a gasification technology operating at the Waste Management Center here in the city. Chemco has a number of access mats that we've actually shredded up and made good quality biochar out of. MyTax is a research group that operates with universities. So my PhD engineer that works with me now and does our computational fluid dynamics, his first project with us was through MyTax, and then we hired him on after that with some support from IRAP, the Industrial Research Assistance Program. Natural Resource Canada, so the NRC sponsors IRAP, and we've got some testing done at the Canman Energy Center as well, I believe. The University of Alberta we've worked with, and TTS is a biocomposite group out of Edmonton, part of which they had a hand in the biocomposite group out in Drayton Valley that does the hemp and biomass mats for different applications. And then obviously the Clean Energy Technology Center and CTEC West out of Calgary, which is a terrific association as well. So now into a little bit more of my expertise, which is IRSI specifically. So I'll just kind of run you through our background and when we got started. So as I mentioned earlier, we started operations in 2014, and that was following my completion at NATE in the alternative energy program. As I mentioned, that capstone project that we ran in our fourth semester got us an updraft gasification system and gave me the insight that there was a real opportunity here for us to add some innovation to the way that we manage waste streams here in Alberta. We've to date operated 6 thermal treatment technologies, 4 of which have been pyrolysis and 2 have been gasification technologies. We have a team of engineers, fabricators, vendors, and laborers that work with us. At any given time, we've got probably about a half dozen to a dozen contracted and full-time employees. We've worked with Alberta Innovates, Initech Alberta, which is their applied research arm, the Industrial Research Assistant Program, which is a part of NRC, NSERC, which funds Engage projects for research projects. We did one with the U of A and Dr. Gupta there in the Chemical Engineering Department, MyTax CETC, U of A, and University of Vigo out of Spain. So Hassan, our computational fluid dynamics engineer, had actually, during his PhD, worked with the University of Vigo, and they had some leading edge modeling that they'd done on this work. And fortunately for us, they were willing to work with us. And coming out of that, we actually had 2 published papers that I'm a co-author on that I definitely do not deserve to be a co-author on. But Hassan did most of that work, and the folks at the University of Vigo helped him quite a bit with that. So we utilize ANSYS Fluent for the computational fluid dynamics. So it's a simulation model You can build into it different technologies, different controls, and we take our geometrical shapes out of SolidWorks and put it into that and then run different processes. So as an example right now, we need to get a heat shield on our ducting next to our control room. So we ran a simulation through ANSYS to tell us how hot it was going to be on the outside of that ducting. And we were within about 25 degrees of the temperature once we actually ran it. So depending on what you're inputting, you can get pretty accurate results. Like I mentioned, we've got 2 published articles and 2 pending. To the best of my knowledge, and I can't say for certain, but to the best of my knowledge, we're the only company operating 2 pieces of thermal treatment equipment the way we are to produce raw biochar in Canada. And I think maybe even the world, but again, that's to the best of my knowledge. So take that with that caveat. So our first design build was what we called the Ulysses. It was a slat chain conveyor, and it was an indirect pyrolysis system that we operated in Drayton Valley for approximately 12 months. It was designed and fabricated by our team between 2014 and 2015. Kind of get a shot of it there. As you can see, that piece of equipment was run off propane. We had a lot of good experiences out in the town of Drayton Valley, and Manny and his team out there were very supportive of us, and they did a lot to help us with the project. Unfortunately, the design of this technology did not work perfectly. So we had a number of lessons learned. As my grandpa has always told me, you don't lose, you either win or you learn something. So we tried to take the most we could out of that process. So some of the lessons that we learned was that thermal efficiency and agitation are key to quality biochar. The 3 things that you need to know when you're trying to make a biochar in a pyrolysis process is how hot it is, how long you have it in there, the residence time, and how much you're agitating that material. The one limitation that we have with the flat chain conveyor was that we weren't able to agitate the wood material going through the process. So that was limiting the quality biochar that we were outputting. While we were in Drayton Valley, we got a voucher through Alberta Innovate's voucher program, and Initech Alberta came out and they conducted a performance validation report for us, and they determined that our configuration was quite inefficient, and again, we lacked the appropriate agitation. So I think that final report from Don and his team at the time told us that we were only using about 11% of our thermal energy. Now, that seems like a huge waste, but with the thermal energy we were using, we were able to produce a fairly good biochar. So that was positive for us. But we definitely sat back and thought we could come up with a better way to configure the technology. So the positive takeaways that we had, we did produce a really high quality biochar. So the biochar that we produced met class 1 IBI standards, which is above 60% carbon. That biochar that you see there in that photo was about 80 to 83% carbon. So really quite a high quality product. When we had the technology running properly, it came out fairly consistent, and we were able to produce fairly high volumes in comparison to other technologies that we've seen out in the market. We got about an 80% reduction of feedstock by weight, and there was an abundance of usable thermal energy that we had at that site as well. That 80% reduction of feedstock by weight, it's a bit of a double-edged sword depending on what you want. If you're getting a high quality biochar, you want the highest amount of remaining biochar possible. So you want to get that reduction reduced a bit lower. So if you can get 30% of your solid byproduct coming out as biochar, that's terrific. But if you're just looking to get rid of waste, so you're not really focused on the production of raw biochar, but rather just treating waste materials, if you can get as high as a 95% reduction, then all the better. You're just getting rid of more of that material.
So this I think begs a little bit more emphasis, because what you're saying basically is out of 100 tons of waste product that goes into it, you end up with only 20% of that as a leftover product.
Correct.
That's huge.
Yeah, for sure. And that thought right there, that's what hit me when I was running the capstone project with Nate was, if we can get rid of 80% of this material, even if I don't have a saleable product on the back end, that seems like a very viable activity to undertake. I mean, we're fortunate here in Canada that we do have a lot of space, but eventually we're going to stop wanting to landfill material. And if we can reduce that material and get some value out of it, it's huge. So absolutely. And that was kind of the genesis for me for sure. So I've talked about our technology, kind of the part that we're at. So let's look at what exactly is raw biochar.
So before you run off, since you were talking about that process, how long does it take to the process from beginning to end?
So our indirect rotary kiln system that we're running now, with about 25 to 30% moisture in the wood material, it's about 26 to 29 minutes to run through that process. Depending on the technology you're using, how much the material is agitated, moisture content, that'll kind of dictate how long that process can be. You can run very fast pyrolysis processes at a high temperature that can fully char material in under a couple minutes. We run closer to the slow pyrolysis process. So part of the balance as well is the higher the temperature you run and the quicker the time, the more gas and liquid fuel you'll get out, the less solid byproduct.
So less marketable biochar after.
Yeah, and there are technologies and there are companies who their focus is not on the solid biochar. One of the companies out of Quebec, Abertech, they run a retort auger, and their focus is on the syngas. So they want to get a usable syngas. For us here in Alberta, you know, we kind of live in the land of oil and gas, so I don't see as much value in that syngas. So we consume it all in our process. We want to get the raw biochar. So the slow pyrolysis process, the longer residence time, the more mild temperatures around 400 to 500 degrees Celsius, that gives us a higher output of biochar. So that's kind of our focus.
Okay. I'll let you continue on with the present. I'll do the rest of the questions at the end of our, because
Sure.
you might be answering some of this as you go on to talk about the current system.
Sure.
Okay.
So the raw biochar. So what is biochar? Biochar has been used for millennia as a soil amendment. One of my favorite stories that I like to tell is when the conquistadors first came into the Amazonian basin, they were driving up the Amazonian River, and they were floored at how densely populated the communities were up and down the river basin. What they ended up eventually finding out was that those soils were so rich and fertile because they were using a biochar process to get what they call a terra preta, or black earth product. This terra preta was essentially a char mixed with compost and all of their other waste materials to get them a really rich fertilizer. And to this day, in that part of the world, that product is still dug up and sold and used as a fertilizer in that area. So this photo here is a microscopic photo. Essentially, what biochar is a big empty hotel. So it's empty space. It's a very porous, anywhere from 100 to 900 square meters per gram of surface area, depending on the type of char that you've produced. And the way that I like to kind of talk about it is that if, say you want to get a high quality soil amendment, you got to blend it with something. So it's not a fertilizer on its own, it's a soil amendment. It adds value to the soil, it helps reduce compaction, helps retain water, gives home for microbial life, but on its own, it's not like a miracle fertilizer or anything like that. The best scenario is to blend it with a compost or blend it with some nutrients, and that's kind of it acts as like a sponge. The empty hotel is what I kind of like to talk about it as. So the pyrolysis process, so kind of going back to some of those questions that we had earlier. So it's high heat in a low oxygen environment. There's a spectrum on the thermal treatment process that goes from flash pyrolysis and gasification out to slow pyrolysis. And then down to torrefaction. So torrefaction starts anywhere over about 275 degrees Celsius up to about 350. Pyrolysis starts anywhere from 350 up to about 800. And then you can get into more high temperatures in gasification and flash pyrolysis up over 800 degrees Celsius. So where we run is around that slow pyrolysis, like I said, about 30 minutes through our process, and we operate at about 400 to 500 degrees Celsius. The real key thing with the thermal treatment is to avoid oxygen in the environment. So you want to prevent any oxygen from getting into our rotary kiln so that we're not actually combusting the wood material, we're cooking it. So we're baking it, we're getting the syngas, we're volatilizing off that syngas, which leads to the porosity and the surface area in the solid biochar. And then that syngas, or that producer gas that comes off, we combust that in the process to drive thermal energy. So if you look at the diagram here at the bottom, you're feeding in material, and this is a diagram, a simplified diagram of our first Ulysses system. So it's not identical to what we're running now, but the concept's very similar. So you run material in, the hearth in the middle is getting heat in from the combustion chamber above it. As that material is cooked, it's producing a syngas, which is being pulled off under the return and then ejected into the combustion chamber and combusted there. Again, as you can see, looking at this, thermal efficiency was an issue. Heat rises, so putting the combustion chamber over our hearth really did make a lot of sense, but these are lessons that we learned through the process. So there's kind of two key classifications that I wanted to touch on just in terms of what are the standards for biochar and what makes a good biochar. One of the issues that I see with the biochar space, pyrolysis, these thermal treatment technologies, is right now we don't have, in my opinion, a very good standard for what a good quality biochar is. So at a surface level, biochar is very simple. It's carbon for the most part, it's porous, it's inert, and it's got a high surface area. But once you dig into it, say you want a biochar for soil amendment, there's certain characteristics you want in that. Say you want a biochar as a feed additive for cattle, there's certain characteristics you want in that biochar. There are guys that I know who are working with biochar as precursors for activated carbon production to actually get into supercapacitors on the cathode and anode to increase the surface area and improve the efficiency of those products. That's a totally different ballgame. You want CEC, you want different applications in your biochar. I know guys who are looking at biochar as a precursor for graphene production. Again, different characteristics that you look at. So one of the things that I'm hoping out of the work that we're doing and the other guys working in this space around the world is that over the next 5 years, we see more of these standards being adopted and accepted by everybody, and it becomes more of a fungible commodity that if you're producing biochar in Australia, it's comparable and measurable against biochar produced here by us in Alberta. So as you can read through here, the IBI and the European Biochar Certificate have very similar definitions of what biochar would be produced in a low oxygen environment from a biomass material. So the CFIA and the OMRI are two certifications that we're pursuing right now. So the CFIA doesn't have specific categories for biochar as a soil amendment, and the process takes about 6 to 18 months. We're about halfway through, and it looks like by October we should have an answer. I'm pretty confident that we'll have our CFIA approval, but we don't have it quite yet. The OMRI, our process was about a month, and we do have a certificate for our raw biochar as an organic product. So the way that we got this testing done was we worked again with Initech Alberta through a micro voucher to get about a 35-page detailed report with everything from proximate and ultimate analysis, metal content, termination bioassay, PCBs, hydrocarbon analysis, chlorine content, dioxins, furans, particle size, bulk density, all of these things. So very exhaustive, detailed report testing pretty much everything you could test in our biochar. And that's what went into both these applications for the CFIA and the OMRI. So the different applications and benefits. So some of you, if you're familiar with biochar, have seen presentations, you might have seen this image on the left here. So these are some of the benefits that you get both for the soil and for the atmospheric benefits. So again, some of these that I've probably touched on, reduces emissions, controls odor, adds carbon back into the soil, and will help retain nutrients and other applications. The specific applications that we've identified that we've worked on out of this list on the right, we've looked at soil amendment applications. We've had our raw biochar run through an activation process to get an activated biochar. We've produced a lignin biochar blended pellet that had 30 megajoules per kilogram of energy density, which is on par with coal. So we've been able to do that. We've used our product as an absorbent in animal bedding applications in a trial setting. And we've also done some filtration applications for cannabis production, actually, for filtering out terpenes to control the smell. We've also done the pozzolan replacement in concrete. And then there's a few other applications that we haven't specifically worked on, but have been identified or trialed by other companies around the world. So the thermal energy system that we're running at our site. So you can see the big black box there in front of you is a gasification system that is a very straightforward, fairly easy to follow technology. So we feed material in where the gentleman sitting on the conveyor is at. That's a gravity-fed airlock, so it prevents air from getting into the system through that. That drops onto some static grates that we then fire with one propane torch. Once we get a burn going in that process, the gas that comes off it is combusted in the process and drives out the top of that stack on the left. Pretty straightforward. Our goal with this is to get rid of lower quality waste streams and produce thermal energy that we then use at the site. So this is the distinction of our process. So if you remember the photo I had of our first piece of equipment, we were running a big propane bullet. This essentially has replaced that propane bullet. So rather than using propane or natural gas or any other petrochemical product, we're taking low quality residual biomass that otherwise would be landfilled. We're using that to get our thermal energy and then drive our other process. So the feedstocks that you run, again, lower quality materials, lower quality biomass. So this is a mix of construction and demolition pile, and we pull out some of the material that we can, and we get some of that lower quality wood material and some of those lower quality biomass streams. We shred them, we process them into the right form, and then that's what we run through the gasification technology there. The outputs, so you get a low quality char. It's got a lower carbon content. It's got a much higher ash content, in part because there is a partial combustion process taking place, but also because the original feedstock has a higher ash content. And then there's higher levels of contaminants within that material. And there's some lower value applications for it. Could go into an ADC, some blends into like a concrete application or something along those lines. But typically this is a pretty low quality product that doesn't have a lot of usable value. What we do get out of it that we can use at the site is the usable thermal energy. And if we had a technology or somebody who wanted to bring a technology to the site to produce electrical energy from that thermal energy, we'd be willing to entertain that. We're not doing it because it's a little bit out of our swing zone, but we have entertained some conversations with companies who would be interested in doing that. Also leads to some greenhouse gas offsets and overall reduces your tippage fee at the landfill. So the biochar production system that we're running at the site right now is an indirect pyrolysis. It's a double rotary kiln system, and this is just a SolidWorks engineering model. This was actually used in our CFD simulation model. So this system is the two kind of tubes in the middle and the bottom left of that image. Those are rotating kilns that we input material into. The rotation increases the agitation. So that's how we improve that agitation from our first piece of technology. By rotating the material, it's constantly moving. So it's constantly exposed to more heat. The other thing that we did through that process to improve upon our technology was the thermal efficiency. So rather than having our combustion chamber sitting above the area where our pyrolysis process is taking place, we have the combustion chamber or the heat box right around. So we're getting an even thermal distribution, and we're getting a better temperature profile through that system. So feedstock, a bit different from what we'd run through the gasification system. This is the clean wood. So this is agricultural residues, byproducts that come out of agricultural sites. We've run hemp, we've run herd material. One of my partners is a farmer in the Ponoka area, so we've run some canola. We've done some different tests with that sort of material. And then what you see here. So some of the sites that All West will be on, there will be some trees they have to dig up, and they'll separate out those materials, and that's what we get. If we can pull out clean wood material from construction and demo piles, we'll do that as well. Access mats, so Chemco has a number of access mats. We've shredded that up, done some testing. Those produce really good feedstock for a biochar process. You can also take like pallets, you know, from department stores. A lot of those end up, once they're broken, they're just thrown away. We could shred that down and we could process that. We haven't run things like railway ties and other contaminated materials, but there are some journal articles that demonstrate that you can get a decent quality biochar in a two-step process. So that's something down the road that we would look at doing as well. But right now, this is the focus of what we're running, the clean wood through our indirect pyrolysis process. And then the output. So again, the raw biochar that we get, usable thermal energy, greenhouse gas offsets, and the tippage fee saving. So this is one of my favorite photos of the work that we were doing when I was still at NATE. And as you can see, you get a fairly decent quality biochar from the wood material there. So just kind of a pointer, if you guys ever play with biochar, a good quality biochar will be fairly matte. It won't be very shiny because you've got all the volatiles off. If you crush it, it should be pretty brittle. And if you dust your hands, you'll be able to get it off fairly easily. That's kind of an indication that you got a pretty good biochar, and it shouldn't have any smell. If you get kind of a sour or a nasty smell coming out of it, there's still some volatiles in there. So it should be a pretty dull smell. So if you ever see anybody working with biochar sticking their nose in it, that's probably what they're trying to do. And then, so how did we integrate these two systems? So these are photos right from our from the bay that we're in at the park. So on the top left there, you can see when the first piece of gasification technology came, it was just a box. Everything else around it, we built and put in place. We put it on a stand. The stack came with the system. We put that in place. Everything in blue in the top right photo, we built. We had a fabricator that we worked with who's terrific. He's out of the Pinoak area as well. And he's done a lot of terrific work for us. And then the bottom left here, you can see the integration of the gasification system on the right and the silver ducting being connected to our indirect pyrolysis process. And then the bottom picture in the bottom right, you can see that all kind of completed. And I think I would have taken that picture probably about a week and a half ago. We're a little bit further ahead now. And our goal here, if all of this virus stuff hadn't happened, by now we would be producing and we'd be inventorying biochar. But by next week, we'll be driving heat into the indirect pyrolysis process, and we'll be kind of going through that hot commissioning phase. So the one other thing that I did want to touch on with the integration of the technologies, how were we able to do this as quickly as we were? A lot of it came down to the computational fluid dynamics. So in the top left here, you can see the model that we ran with the gasification system to determine our thermal energy. So on the right there, you can see the grates where the heat is combusting on the biomass material as it enters the area. The red lines going across is where the highest heat is, and that's because that syngas is being produced and it's being fully combusted in that hot temperature. And then as it hits the stack, it's picking up speed. And right in this image, it's just being emitted to atmosphere, but we will tee it off through that port on the side that'll direct the energy into our indirect pyrolysis process. And then if you look down on the bottom right, that's a shot of the ducting coming into our indirect system and heating up an even temperature profile. So this is exactly what we want to see in terms of our indirect pyrolysis process. We'd like to see a bit of a cooler temperature profile on the intake, and then it heats up as it gets to the output or the discharge end of the system. That is part of the process for heating the material. In lab settings, you want to control that heating rate. It's a little bit harder to do at a full pilot scale, or sorry, a full commercial scale. But if you're able to do it, you can improve the quality of biochar that you output. And so what we were able to do with this CFD modeling was position our ducting, position our exhaust ducts so that we can control that thermal profile. If we weren't able to test this in a simulation model, essentially it'd be trial and error. We'd have to build something, see if it worked, and if it did what we wanted, great. If not, we'd have to go back to the drawing board. So I really wanted to emphasize the computational fluid dynamics, and the engineer that we have working with us have added a tremendous amount of value to our work. So the markets that we have access to or that we're pursuing, this covers off what All West is after, what we're after, and what Nelson Environmental Remediation is after. So as you can see, the total approachable markets through Alberta and North America is about $6.5 billion. Obviously, we're not going to be able to access all of those markets, but waste diversion in Alberta alone at $70 a ton is under $300 million a year. Biochar, based on the studies that I've looked at, not including China, but North America and Europe, is about $160 million a year in terms of value. Soil remediation in Alberta alone is $2 billion worth of addressable market. And activated carbon globally is about $4 billion. It says North America under activated carbon, that should be global. It's about a $4 billion global market. So if we can get our raw biochar into an activated process, there's a tremendous amount of opportunity there as well. So a couple things that I kind of did touch on already, but specific trials that we've worked on, like I mentioned, we got the biochar pellet, comparable energy density to coal. We've done the air filtration. We have had successful trials with our raw biochars and organic growth medium for cannabis. And we've got a couple of other applications that we're working on right now. We've done the bedding as an absorbent for chickens. We've done some pozzolan replacement, so replacing the aggregate that goes into the concrete, so using our biochar as a replacement for that, and has been very successful. And then we've done full germination bioassays for soil amendment, so our raw biochar has been able to show that you can grow food in it quite well. So right now, we're right in the process of launching our first product. So this is the packaging for our raw biochar. Again, had the virus not taken place, we'd be bagging up these packages and hopefully looking for home and garden shows in the spring here. It's being pushed out probably till about the middle of the summer, but we've gone through this whole branding activity and had a terrific firm working with us on this. And so this will be the package, hopefully, that you guys will be able to find in the supermarkets at some point here in the future. So Biochar price, there's wholesale versus retail, and the price will range. Tom Miles, who's the executive director of the USBI, did a good presentation that he was very gracious to share with me. Tom identified that you're going to range from about 16 cents to $2 per pound, or about $312 to $4,000 a ton for wholesale product of biochar. Again, that depends on a number of things, characteristics of the biochar, what's its application for, and a number of other things that would go into that. The last report that I saw from the IBI in 2016 found the average price around $3,300 per ton Canadian. These are all Canadian prices. I had to do some conversion because Tom's American. And then the low volume retail packages. So for some of the guys who are selling 1 kilogram bags in the store, that'll be as high as $13 per kilogram. So you can get quite a high return if you're selling those lower volume packages versus the retail packages versus the wholesale by the ton. So that was about everything, guys. I hope I didn't talk too fast. I hope everybody could follow along. I've shared this link with Mark and Heather, and I have no problem with them sharing it with you guys. My contact info is there. You can look at IRSI at irsi-inc.com, All West Bioindustrial Park, awbip.com, and that's my cell number there as well, and my email. Feel free if you got any questions or anything you're curious about. I always like to chat.
Thank you so much, Chris. That's absolutely wonderful. Boy, you know, my mind's going a mile a minute now with everything that you've talked about. And I was scratching out ideas, like discussion points, like crazy. But then the attendees have also been coming up with all sorts of questions for you. So I'd like to take the next 15 or 20 minutes just to go through any questions we might have. So one of the questions that came through, what is the end result use of the biochar at this point? Like right now you mentioned soil amendments. Is there anything else that you're going towards?
Yeah, so soil amendment for us is what I would call the lowest hanging fruit. So we've produced and we have the certification from OMRI and we're waiting on it from CFIA. But we can bag up and sell material. So that would be kind of the main thing for us. Next past that would be, there's a terrific study going on in Southern Alberta in cooperation with the University of Lethbridge, actually feeding biochar to cattle. And international studies have shown that it reduces their methane emissions by 28%, helps bulk the animal by about 25%, and improves their feed efficiency and health. So they're trying to replicate those studies here. That could potentially be a huge opportunity for us. I did mention the bio-coal, the coal replacement, the pellets we produced. On paper, they're comparable with coal. The product or the problem for us is that it's volume. To produce enough of those bio-coal pellets to even do a trial is a scope way higher than we'd be able to access. So there are really interesting opportunities that I would like to pursue, but we got to be able to kind of measure, you know, which ones can we go after. So the soil amendment is definitely the first one that we're pursuing now.
Awesome. And so a little question that might be slightly off topic, but you know, when we talk about waste streams, I think it's very relevant. So with all the extra waste plastic now available through the inability of municipal recycling to take it all now, do you see that there's a ramp up on creating energy gases or alcohols, like is being done by Enercam, being viable at reasonable costs per ton instead of this waste plastic being landfilled?
Yeah, so my limited experience with plastics is I really don't work with them too much, but the complexity in plastics is that you end up with those 9 polymers. And I know a lot of recycling processes require you to be able to separate out different polymers, which becomes very difficult to do. So a viable application could be producing a liquid or a gaseous fuel from those plastics. I don't have a lot of experience with it, and I'm not aware of too many companies that are specifically doing it. But I did have a conversation just recently with a gentleman who's looking to actually shred all the different polymers and produce essentially a recycled plastic from that shredded material. So there are some activities that I've been aware of but not necessarily specifically looking at the gas material or liquid fuels coming out of it.
Okay. Is there a recipe that works better than other biomass as feedstock? So for instance, if you had a mix of material, is there like the perfect kind of components that you need? And then yeah, so let's start with that question.
Sure.
Recipe that works better than other biomass as feedstock?
So I would say in my experience, it's been typically like hardwood material has produced the best quality biochar in my experience. Typically what you want is the lowest ash content possible and chip to whatever appropriate size. The less moisture you have in the material, the better off you're going to be. But in terms of different types of biomass, which works best, it kind of depends on what you're looking to output. So what are the characteristics in the final product? That's another part of the work that we're trying to be the spearhead of as well, is helping to correlate the relationship between the characteristics in the feedstock, the operating parameters you go through, and the characteristics in the biochar. I'm sure there are a lot of people who've done a lot of that work around the world, maybe just information that I haven't been able to get access to. So that's something that we're regularly doing as well. And Innovator Alberta is a big partner with us on doing that. So every time we run a new type of material, we get a test done on that feedstock, and then we get a test done on the resulting char that'll come out on the back end. So we've been doing that over the last year with both the gasification technology and the smaller bench scale system that we were working with previously.
That's awesome. You must have data out the wazoo with all that. Holy moly. Does biochar act as a good precursor for carbon fiber production?
Yes, it can. And so we haven't looked, our company hasn't looked specifically at like carbon fiber applications, but we have provided our material to an activation technology company. And so they've taken our product, they've run it through a high heat, a low toxicity chemical process, a hybrid activation process, and they've got a resulting activated biochar with a 65% yield rate at about 2,100 square meters per gram, which is about 1,000 square meters per gram higher than traditional activated carbons that are on the market now. And they're right now, just a conversation I had last week with them, they're looking at getting their activated carbon into carbon fiber applications. I've also talked with a company out of Ontario who is looking to source biochar for graphene production. So they're scaling up right now to produce graphene, and they have a need for about once they're scaled up, about 10,000 tons of biochar for full-scale operations. And their goal is to produce graphene. So there's a lot of really interesting different carbon products that can come out of a biochar for sure.
Yeah. Hey, could you stop sharing your screen? That way we can get everybody up on the screen.
Absolutely.
And so one of the questions I had written down was, you mentioned activated charcoal or biochar for a couple of times. What does it take to activate the biochar?
Yeah. So for us, it would be a two-step process. So we'd run it through our pyrolysis process. We get a raw biochar. And then what we would apply would be a physical activation process. So we'd get up to about 1,000 degrees Celsius for a short amount of time. We'd blast that raw biochar with that high heat. And then typically you would expose it to steam or CO2, which would further expand out the surface area and give you a higher porosity. You can do it with chemicals as well. So a chemical activation process, you blend in a chemical, you add some heat, but the result of that is that you have to kind of wash out the chemicals. If you're lucky enough, you can recycle them. It'll get you a bit of a higher quality activated product, but it's a little bit more involved. So our focus would be on like a physical activation process where we get that real high heat, blast it with some CO2 or some steam, and then we get kind of a steam exploded or a CO2 exploded surface area, which would result in an activated biochar.
Okay, cool. And so is that something that you're working on late? This is a later on project for you, or is that something you're actively working on right now?
Tom and I are actually talking with a company that their headquarters are out of Edmonton, and their chief technical officer works out of the U of A. And so we're actually looking to see if we can license their technology to deploy it at our site.
Okay, cool. Now, I was interested in that idea that you had the gasification process, which created the energy use for the pyrolysis. Is there a way, have you looked into a way, is it possible to take waste feedstock that is not great and put it through gasification first and then use it through pyrolysis? Or does it have to be a pure product on the onset?
Yeah, you could. Part of my reluctance to do that would be if you're running it through any sort of combustion process, which typically a gasification process has a bit more oxygen in there, so you're getting a bit more combustion, you're going to end up with more ash in that outputted product. Getting rid of the ash is essentially anything you can't combust. So if you have more ash in your feedstock going in, it's going to come out in your end product. And that's one of the things that you want to try to minimize when you're producing a good quality biochar. So it could be you could run that process. I just don't know that it would add a lot of value.
Yeah. And so another question that came up was, is there a process to pre-dry the feedstock to reduce the moisture content first?
Yeah. So the company out of Quebec that I mentioned, Abertech, Peter, their CEO, they actually won't sell their technology without a drying system on the front end. So they require that you get your feedstock going into about 5%. Because of the setup of our equipment and the fact we're pulling thermal energy from essentially a waste product, we're not too concerned about increasing that residence time. So we're not drying our material going in, but absolutely, you'd be advised to, if you could, either keep your material as dry as possible, or like you said, run it through a dryer on the front end. To get it down as low as possible, because that definitely will take a lot of energy just to get rid of the moisture.
Mm-hmm. Oh, that's really interesting. So are you thinking about any other kind of waste product? What about organics and that sort of thing over the long haul?
So part of it's scenario and the context. So because we're working with All West Demolition, they don't handle that sort of stuff. So we're not looking at that right now. But absolutely, that's biosolids, MSW, a lot of those other waste streams that can run through a gasification or a pyrolysis process. But it's not something we're focused on.
Yeah. Okay. I don't.
Question, Mark, is could I jump in?
Sure, please.
Chris, thank you very much for the presentation. Does anyone have an update on a process that was going on here north of the river a couple of years ago? A fellow there was trying some controlled wood burn systems there, I think, to make biochar. Is there any update on that? I think it started with a walk the talk thing.
I think Brian could speak to that. Yeah. Brian, do you want to unmute yourself?
Sure. There was two different processes involved with that particular site. One was, I think, through one of our counselors, Blake Adams. He had a machine that was portable, and it took wood waste and basically reduced it to what he thought was a version of biochar, but it really wasn't. It was just more or less ash. And the machine was good for clearing land that, they wanted to use for other purposes, but I don't think that the machine itself was anything other than reducing the volume of waste material to go to a landfill. Chris's option is obviously the far superior, because he's hoping to get an end product from his process. And I think the other idea that you were referring to was the green powerhouse, the greenhouse that was talked about that currently exists in Montana. And I think there's basically very similar processes involved. Chris is much farther ahead in terms of the proving of that technology in a sense, because there's one operating in the US, and I think there's some challenges with getting it to North America, but we're hoping to get an update on that from Kari in the near future. But what I see as a possible fit here is that Chris is taking the wood waste construction debris, whereas Kari, I think, is looking at other types of waste materials, including organics and coffee grounds and that sort of thing, which obviously, as Chris indicated, needs a dryer on the front end to make that material available to her system. So I think there's some merit in both of them, but I think, correct me if I'm wrong, but I think those are the two that you were referring to north of the river. Is that correct?
Yes, Brian, I think that was it. Thanks very much.
Terrific. So Chris, another question that came up is about the raw material. Will you have enough raw material to reduce your anticipated demand for over the next year?
Yeah, so it's more, we'd have enough material coming into the site. The more clean wood material or clean biomass that we can sort out, the better quality biochar we'll get out of it. Part of what we need to really get our head around is, I think with everything operating, we can produce around 1,200 tons of biochar per year. Will I be able to move 1,200 tons of biochar in 12 months? I'm not 100% sure.
It's a lot of bags and a lot of garden.
Yeah. So we get about give or take 250 kgs per cubic meter bag. So we're talking about, 4,000 to 5,000 cubic meter bags in a year. How big is the market for that? Honestly, I showed you some numbers, and I did a lot of work to actually drill into those numbers and find out exactly how much material was being moved. It's really hard to say for certain, though. And again, a lot of it comes down to it's not a fungible commodity. My biochar is not necessarily going to be the exact same as somebody else's biochar. So it's a bit tough, and you really have to identify the right partners to work with. And so feedstock coming in, we've got a handle on. We've got enough material from All West, and we should be able to have an effective process going through that. A bigger question for us is how many tons of biochar can we move? So,
yeah. I think, Brian, you have a question?
Yeah, just to clarify then, your current process you find is ideal to produce the biochar for soil amendment. Is that right? Your recipe, if you will?
Yeah. That soil amendment would be that kind of that. We're shooting for above 70% carbon. We probably won't get much higher than 80, but we want to be in that 70 to 80% carbon range. And then depending on what application, but a lot of it is, we have to work with the supply chain. So any guys that I talk to, if they call me inquiring about biochar, I really need to know what they're looking to get out of it. So I really want to encourage being able to develop that conversation and make sure that, the guys that we're working with, I'm giving them, what I'm giving them has been tested. They know what it is, and hopefully it's suitable for their applications. And if it's not, I don't want to sell somebody something that's not going to work. I think a lot of the headache that people have created for themselves in the pyrolysis space over the last couple of decades is selling people product, saying it's perfect and it can do everything they want, and then it doesn't work, and kind of shoots us all in the foot. So I want to avoid that as much as possible. But a lot of dialogue with any clients that we have is definitely very important at this point, for sure.
So you can actually adjust your recipe to suit your end client ultimately at the end of the day.
To an extent, yeah, for sure.
Thank you.
So Chris, one thing that I'm really interested in, you're in an emerging emerging technology space when it comes to waste to energy and waste remediation or reduction. And could you talk a little bit about how it was for you to be able to take this idea? You took it to Drayton Valley, you learned some lessons, you brought it to Edmonton. Can you talk a little bit about what that space looked like as far as finding funding, as far as finding support? You made it sound all so very simple, but I'm absolutely sure that at some point you were pulling out your hair going, God, it's got to be a simpler way to do this.
Yeah, I had a few of those, oh gosh, what am I doing moments for sure. Yeah, so my background in sociology and a lot of the communications work I did in my undergrad, I got really good at writing grant applications and putting proposals together, so that helped a lot. And I was fortunate with the group that I worked with. I had two really good partners from the get-go that had a lot of faith in what I was doing, and they provided the private capital to get us started. Again, I was able to match that with public funds, both in the form of grants and tax credits. So that helped a lot, but definitely it was a hard grind. Being out in Drayton Valley, what was tough, it was tough driving out there every day, not knowing if the technology was going to work, and getting up at 5 so I could get out there for 7. But yeah, it's been a great process. All of the headaches that I've kind of suffered through, I think have gotten us to the point that we're at now. So I wouldn't trade it for anything. But yeah, it definitely was. you know, a lot of it was going into conversations and meeting new people, much like things like this, and you know, even being introduced to Tom when I was out in Drayton Valley, and then later at Devon. You know, that was just coincidental, and a guy like Tom's been a huge supporter and has played a key role in a lot of the stuff that I've done since then. So, you know, meeting the right people and finding the right network played a big part of it. And doing my best to recognize the things I wasn't good at, which there's more of them than I'd love to admit. So being able to find the right team around me definitely played a big role for sure.
So you need a sense of humility.
Yeah, definitely need a sense of humility. And having a trusting, loving wife definitely helped a lot as well. So anytime I was kicking myself, she was usually there to make me feel better about it. So
Nice. Really good. Any other questions from the group? Chris, I can't thank you enough for doing this for us. We had this idea. We had to defer all the live events, and then we emailed everybody and said, terribly sorry, we have to postpone. And then last week we had the idea of, hey, I wonder if somebody would do an event. And so, Chris, thank you so much for presenting to us today. This idea of biochar and your pyrolysis system gives us a lot to think about. In the context of our waste streams, and I can't wait to see how this technology evolves to the point where organics is part of that. I know that we had Dr. Ashbolt a couple of years ago speak to our group, talking about black water and gray water separation at source, and then taking black water and then being able to separate out solids and that sort of thing. We've talked about the potential of using agricultural products, so the waste streams from livestock, and being able to turn that into energy as well. And so it's thrilling for us to hear that what happened in Drayton Valley wasn't failure. It was, like you said, a lesson learned, and you're able now to bring it out here and able to then apply that learning and do something magical here on our doorstep. So thank you very much to do that.
Yeah.
Just so you know, Chris, we are going to be planting a tree in your name as a thank you. It's something that we have decided as Walk the Talks, that is part of our Walking That Talk, is that we like to thank our presenters by planting a tree in your name. So maybe in 100 years you can cut it down, and that could be the next feedstock for your biochar.
Awesome. I really appreciate that. And thanks a lot, Mark. And also I wanted to throw it out there, once all this craziness settles down, we definitely, I'd be open to arranging if you guys wanted to put together a group and come out one afternoon and take a tour of the system. I'd be more than willing. I'd love to have you guys out. So
yeah, I know we could probably fill up the Devon bus a couple of times over, I think.
Right on. Perfect.
Chris, thank you very much.
Thanks, guys.